Let us examine the IUPAC classification of pore sizes. A micropore has effective pore diameters smaller than 2 nanometers or 20 angstrom. A meso-pore has pore dimensions in the range of 20 to 50 nanometers, and a macropore has pore sizes in excess of 50 nanometers. Let's examine the energy of interaction of gas molecules with the pore wall. This graph presents calculations using the Lennard-Jones 612 potential. For hydrogen, the potential energy of interaction is shown by the black lines. For argon, the interaction energies are shown in blue, and for methane, the interaction energies are drawn in red. R is the distance from the wall, and for each of these gas molecules, sigma is the size parameter and epsilon is the energy parameter. The sigma for hydrogen is smaller than the sigma for argon, and the sigma for argon is smaller than the sigma value for methane. Close to the wall, for smaller values of R, repulsion forces are dominant. Further away from the wall, attraction forces come into play, and the depth of the energy well is dictated by the epsilon or energy parameter, which is largest for methane and smallest for hydrogen, reflecting the stronger absorption of methane with respect to argon, and argon is stronger in its absorption strength than hydrogen. We note that at the distance of 1 nanometer from the pore wall, the potential energies of interaction are close to zero. Therefore, for meso-pores with effective pore sizes larger than 2 nanometers, there is a central core region in which molecule-molecule collisions are dominant and molecule wall interactions are of negligible importance. Conversely, for micropores with pore sizes smaller than 2 nanometers, a gas molecule remains within the force field that is experienced with a pore wall. There is no central core region for micropores. My talk today is on the diffusivities of unary gases inside micropores. The unary diffusivities of gas species in micropores can be determined from experimental data on transient uptakes inside crystals of zeolites or morphs, from pulse field gradient NMR techniques, or from molecular dynamics simulations. There are 3 types of unary diffusivities that are determinable: Fick diffusivities, Maxwell-Stefan diffusivities, and self-diffusivities. And I will talk today about the interrelations between these diffusivities. The theoretical background to the material I will cover today are provided in 3 publications of mine that are listed here. Watch also my video presentation, Diffusion in Ordered Crystalline Microporous Materials, on my YouTube channel. To start the discussions, consider a set of experiments for adsorption and desorption of ethane in LTA4A zeolite. The experimental data show asymmetry in the adsorption-desorption characteristics, and we shall examine the reasons behind this. We start our discussions of adsorption-desorption asymmetry by considering the experimental data of Garg and Ruthven for transient adsorption and desorption, denoted by the red circles and green squares respectively, for uptake of ethane in LTA4A zeolite. 4A zeolite consists of a structure made up of cages, approximately 11 angstrom in diameter, separated by windows of dimensions that are approximately 4 angstrom. Note that the sodium cations, of which there are 96 per unit cell, the sodium cations partially obstruct the window regions, and they influence the intercage hopping of gas molecules. Let's examine and analyze the adsorption and desorption kinetics by first resorting to the Fickian diffusion model to describe intracrystalline diffusion. Let's adopt the Fickian model to describe intracrystalline diffusion of ethane in LTA4A zeolite. In the Fickian model, we assert that the intraparticle flux, denoted by n sub I, is proportional to the gradient of the molar loadings, Qi. And this is the partial differential equation that relates the transient uptake to the intracrystalline diffusion fluxes. If we assume that the Fickian diffusivity is independent of the loadings, the partial differential equation describing uptakes can be solved analytically, and the expression for the spatially averaged component loadings can be expressed in this form. This is the Geddes model used for a variety of applications, such as in distillation, absorption, extraction, also for transient uptake in spherical crystalline materials. Using the experimental data, we can back out the diffusivities, the Fickian diffusivities, for the transient adsorption and transient desorption. If we do that, we can determine that for describing the transient adsorption kinetics, the the Fickian diffusivity divided by the square of the crystallite radius is 1.1 times 10⁻³ per second. However, for the desorption cycle, the experimental data is described by the value of the Fick diffusivity divided by RC squared equal to 6 times 10 to the minus 4. Put another way, there is an asymmetry in the adsorption and desorption kinetics. The adsorption kinetics appears to be faster by about a factor 2 as compared to the desorption kinetics. So let us examine the reasons why the asymmetry occurs. And to do this, we have to adopt a more fundamental approach to intracrystalline diffusion by properly recognizing that the driving force for intracrystalline diffusion is not the gradient of the molar loading, but rather the gradient in the chemical potential. If we adopt the Maxwell-Stefan diffusion formulation, the intracrystalline flux Ni is written in terms of the gradient of the chemical potential in this manner, where Qi is the molar loading of component I, R is the gas constant, T is the temperature, and we have the chemical potential gradient of species I. If we compare this expression with the Fickian expression shown on the previous slide, we can derive a relation between the Fickian diffusivity D with the Maxwell-Stefan diffusivity D with a line through it, and the relation shows that the Fickian diffusivity equals the Maxwell-Stefan diffusivity times a thermodynamic factor. The thermodynamic factor is determinable from the adsorption equilibrium that relates the molar loadings Qi to the partial fugacity in the bulk gas mixture F sub I. If the adsorption equilibrium is described by the single site Langmuir model, Qi divided by Qi at saturation, which is the partial occupancy, is the Langmuir constant times the partial fugacity in the bulk gas mixture. And we can determine the thermodynamic correction factor to be 1 divided by 1 minus theta, but theta is a fractional occupancy. And if we examine how the thermodynamic correction factor depends on the fractional occupancy, we note that at zero occupancy or very low occupancy, the thermodynamic correction factor is unity. But as the occupancy increases and approaches unity, the thermodynamic correction factor increases exponentially in this manner. During the adsorption cycle, we proceed along this way, and in the desorption cycle, the thermodynamic correction factor decreases because the occupancy is progressively reduced. Now, if we examine the Fick diffusivity and equals to the Maxwell-Stefan diffusivity times gamma, we note that in the adsorption cycle, the Fick diffusivity would increase with fractional occupancy, whereas in the desorption cycle, the Fick diffusivity would be a decreasing function of the fractional occupancy. And the adsorption and desorption cycles can both be modeled reasonably accurately with the value of the Maxwell-Stefan diffusivity divided by the square of the crystalline radius equals 2 times 10 minus 4. And the reason that the adsorption kinetics is faster is due to the influences of the thermodynamic corrections. And using the Fickian model, we have to account for the faster adsorption kinetics with a Fick diffusivity divided by RC squared value of 1.1 times 10 minus 3, and the desorption cycle is described by the Fick diffusivity divided by RC squared value of 6 times 10 minus 4. The asymmetry is engendered by the behavior of the thermodynamic correction factor. Taking due account of thermodynamic corrections, both adsorption and desorption cycles can be described by a unique value of the Maxwell-Stefan diffusivity divided by RC squared equals 2 times 10 minus 4. And this underscores the importance of using a more fundamental description of intracrystalline diffusion. Further background information is provided in this publication. See also my videos on diffusion in ordered crystalline microporous materials on my YouTube channel. The Maxwell-Stefan diffusivity that characterize molecule wall interactions can also be obtained from molecular dynamics simulations by monitoring the mean square displacement of an ensemble of molecules. The formula for calculation of the Maxwell-Stefan diffusivity for species I in one of the coordinate directions is given here. In addition to the Maxwell-Stefan diffusivity, MD simulations can also be used to determine the self-diffusivity by analyzing the mean square displacement of individual molecules. The self-diffusivities reflect a combination of molecule-molecule and molecule-wall collisions. Using the Maxwell-Stefan diffusion formulation, we can derive an expression that relates the self-diffusivity to the Maxwell-Stefan diffusivity. The relation is provided here. This coefficient here is a self-exchange coefficient. And if we examine MD data for the diffusivities of hydrogen and CO2 in MFI zeolite, we see that the Maxwell-Stefan diffusivity is higher than the self-diffusivity for both hydrogen and for CO2. The self-diffusivity is lower than the Maxwell-Stefan diffusivity is because individual jumps of molecules are correlated due to revisitation of sites that have been recently vacated or abandoned. The MS diffusivity, reflecting collective motion of molecules, is free from such correlation effects, and are amenable to simpler interpretation and modeling than the self-diffusivities. PFG NMR experimental procedures also are used to determine the self-diffusivities. So for use in practice, we need the Fick and Maxwell-Stefan diffusivities, but often it is easier using PFG NMR techniques or even MD simulations to determine the self-diffusivities of molecules, but the self-diffusivities of molecules reflect both molecule wall and molecule-molecule collisions and are more difficult to interpret. There is, however, a scenario under which the Unary Maxwell-Stefan diffusivity can be identified with the Unary self-diffusivity. To illustrate the scenario, let us consider the diffusion of methane in LTA4A zeolite that consists of cages of 743 cubic angstrom. Each cage is separated from adjacent cages by narrow windows of 4 angstrom in size. The guest molecules such as methane, hydrogen, CO2, nitrogen jump one at a time across the windows. To illustrate that, let's look at animations determined from MD simulations. We see the methane molecule jumps one at a time across the window, and the jumps are uncorrelated. Since the correlations are negligible, the self-diffusivity can be identified with the Maxwell-Stefan diffusivity. Generally speaking, the self-diffusivities can be determined to a significantly higher level of accuracy than the Maxwell-Stefan diffusivity from MD simulations. The Maxwell-Stefan diffusivity are subject to more numerical errors, and long simulation times are required for accurate determinations of the MS diffusivities.